SwayamPrabha. Digital India. Educated India.
Okay, so now having obtained a big picture viewpoint of what we are going to study in this particular course, let us have a brief recap of what mathematical tools like that we would be requiring. Okay, as we discussed, like we are going to deal with what we call as single input, single output, linear time invariant, causal dynamic systems, right? That we are going to characterize using spatially homogeneous, dynamic, continuous time, deterministic models. Typically, these models take the form of an ordinary differential equation, right? So the first sort of mathematical tools like that we would require for this particular course is the what to say is a basic working knowledge of ODEs, right? As we are going to consider like more specifically like linear ODEs with constant coefficients, right? So why linear ODEs with constant coefficients? Like typically what happens is that like the linearity comes into play because we are dealing with linear systems. We are dealing with constant coefficients because of time invariance. Okay, so the concept of time invariance essentially implies that like if we are dealing with ordinary differential equations, the coefficients of the terms, okay, in that equation are going to be constants, right? So that essentially is a consequence of time invariance. Okay, so that's why we are considering linear ODEs with constant coefficients, right? So let us consider some specific ordinary differential equations. Okay, but I suggest that all of us go back and recap what we learned in a first engineering mathematics course on ordinary differential equations, right? Which would really be helpful. Okay, so but I am just going to recap a few important concepts. Okay, that's what I am going to do here. So if we consider a first order what to say homogeneous ODE of the form of this form, let's say like I consider dy dt, okay, plus let's say a y d y t equals 0. Okay, so let us say we consider a linear first order homogeneous ODE of this particular form, okay, where of course a is a constant parameter, right, constant real number. All of us know that the solution to this ODE is of the form like c e power minus at, right? So that's something which all of us know, right? So where of course I can write c as essentially y0. Okay, so y0 is the initial condition. Okay, so this is an initial value problem. So given that the independent variable is time, so I can write the same solution as y0 e power minus at, right? So why do we have an exponential solution to begin with? Like how do we get this? We just substitute y of t of the form e power mt, and then we get m to be minus a, right? So that's how we get the solution for this particular homogeneous linear ODE. And why should we have exponential solutions, and why should we fit an exponential substitute an exponential function to begin with? Because it has been shown that a solution exists for linear ODEs with constant coefficient, and the unique solution takes the form of exponential functions. Okay, so in other words, the exponential function is the only solution for linear ODEs with constant coefficients. Okay, so that's why we are essentially substituting a solution form that corresponds to an exponential function to get this to solve this equation. Okay, so if we have now a first order inhomogeneous ODE, okay, of the form, let us say dy dt plus a y of t is equal to, let us say, some b of u of t. Let us say we have some equation of this form, right. So, what is the solution to this equation? We know that it is going to comprise of two parts. Okay. So, the first one is due to the initial condition. Okay. So, it is going to be y naught e power minus a t, okay, plus integral 0 to t e power minus a t minus tau b u tau d tau. Okay, like see, I am just using the symbols corresponding to our course, right. So, please remember, like for us to keep in focus what we are doing, like we are looking at a system to which we provide an input u of t and an output y of t, right. So, I am writing whatever equations I am taking in terms of the input and the output variables. Okay, so that is what I am doing, right. This is a solution to this particular inhomogeneous ODE. So, we can immediately see that there are two components to the solution. The first part of the solution is due to initial conditions. Okay. So, this part is typically referred to as what is called as a free response. Okay. The second part is a solution due to the input provided. Okay. This response is what is called as a forced response. Okay. So, we see that in general, like we have two components to the output function. Okay, like when we model systems using this class of equations. Okay, like the first part is what is called as a free response, which comes in, like due to the non-zero initial conditions. The second part is what is called as a forced response, which comes due to the input that is provided to the system. Okay. So, given these responses, the point is how do we use this to analyze the class of systems under study. Okay. So, we see that, like once I model the class of systems that we are looking at in this course, we would get linear ODEs of with constant coefficients, right. And then we see that, like given any input, like I can use essentially solutions to the ODE to calculate what would be the corresponding output from the system. Okay. So, that is something which is very important to us. Okay. And in this process, like what we are going to do is essentially use what is called as a Laplace transform that helps us to go from the time domain to the complex domain and essentially convert problems involving ordinary differential equations into problems involving algebraic equations. Okay. So, that they are easier to work out by hand, and then like we take the inverse Laplace transform to come to the time domain, right. So, let us look at what to say complex variables, then we will come back to ODEs, and then like we will see how we use Laplace transform on ODEs and then like process them. Okay. So, that is something which we are going to come back to. Okay. So, we consider complex variable of the form. Let us consider a complex variable S which of the form sigma plus j omega, where sigma is some real number, omega is a real number, and j squared is equal to minus 1. Okay. So, I am just using j, like instead of I. Okay. So, that is what that is how we will represent complex variables. And typically what we will do is that like we will draw what is called as an S plane. which essentially can be used to graphically represent a complex number. So, that will have two axes, like what is called as the real axis and the imaginary axis, and we use this to graphically represent any complex number. Okay. And a complex function f of s is a complex valued function of x. Okay. So, that is what it is. Yes. Okay. And typically we write f of s to be equal to some f r real part of sigma omega plus j f imaginary part of sigma omega. Okay. So, that is a typical split. Okay. So, for example, let us say like we consider like f of s to be, let us say, s squared, right. I can rewrite this as sigma plus j omega whole square. This can be rewritten as sigma squared minus omega squared plus j times 2 sigma omega, right. So, this part is fr of sigma omega and this is fi of sigma omega. Okay. Now, a few definitions, right. A complex valued function f of s is said to be analytic in a given domain if f of s and all its derivatives exist in that domain. Okay, that is very important. Okay. And another definition is that points in the S domain where f of s is not analytic are called singular points or poles. Okay, so that is another example. So, say for example, like if we consider f of s to be equal to 1 by s plus 1, okay, we can immediately note that s equals minus 1 is a singular point or pole okay, of this particular function, right. So, that is an example. Okay. And there are what are called as Cauchy-Riemann conditions, which are essentially used to evaluate whether a given function f of x is analytic. So, what are these two conditions? There are two conditions here. So, the first condition is the partial derivative of fr with respect to sigma should be equal to the partial derivative of fi with respect to omega. Second condition is that the partial derivative of fi with respect to sigma should be equal to the negative of the partial derivative of fr with respect to omega. Okay. So, those are the two Cauchy-Riemann conditions. And another what to say set of equations. Once again, as I told you, I am just recapping what we would have already learned in a basic course in engineering mathematics. I am only writing down whatever is relevant for our course, which we will use as we go along. So, what are called Euler's relationships, like so we know that if I have an exponential with a complex exponential, let us say if I have e power j omega t, I can rewrite it as cos omega t plus j sin omega t, and e power minus j omega t is going to be equal to cos omega t minus j sin omega t. Okay, so that's the Euler's relationships. Okay, from these two relations, we can immediately see that cos omega t is going to be equal to e power j omega t plus e power minus j omega t divided by 2. Sin omega t is going to be equal to e power j omega t minus e power minus j omega t divided by 2j. Okay, so that's the Euler's relationship. Okay, so now moving on, we look at what are called as Laplace transform. Okay, so so what is this Laplace transform? Okay, so let me write down the definition of a Laplace transform of a real valued function f of t. So the Laplace transform of f of t, which is in the time domain, is integral minus infinity to plus infinity f of t e power minus st dt. Okay, so here s is the complex variable. So this is what is called as a bilateral Laplace transform, because the integration is carried out from minus infinity to plus infinity. Okay, so sorry, bilateral Laplace transform. Okay, on the other hand, like in this particular course, like we would use what is called as a unilateral Laplace transform, because typically we are not what to say, we are going to start a process or a what to say, analysis of a system from time t equals 0. So we make the lower limit as 0, and consequently we will go from 0 to infinity f of t e power minus st dt. Okay, so that's going to be the what is called as a unilateral Laplace transform. Okay, so that's the unilateral Laplace transform. So and there's something called as the inverse Laplace transform, which essentially maps any given function in the complex domain back to its function in the time domain. Okay, but typically we calculate the inverse Laplace transform using what is called as a partial fraction expansion rather than using the definition per se. Okay, that's what we are going to follow in this particular course also. So before we move on to use to learn and use how we are going to apply Laplace transform in our particular course. I am just going to point out a few important functions that are going to be useful to us, okay, like in this particular course. And so let me call them as some typical inputs that we are going to look at. Why is this important? Or some standard inputs, more than typical, okay, we can also call them as standard inputs. Okay, so typically, like please note that, like we are going to have an input u of t and we get an output y of t, right? So that's our notion of a system, right? So by and large, like if you want to analyze systems, like and various designs of choices for systems, if you want to have a proper analysis done, like typically we need to give some standard input so that we evaluate the system response, right? If I design, let's say, n systems for an application, right? So I can evaluate them provided I give the same input to the designs, right? So for that purpose, like we use some standard inputs. Okay, let's look at each one of them. Okay, so then we will come back to Laplace transform. So first we will look at what is called as a unit impulse input. So what is this unit impulse input? Let's say okay, this is also called as the Dirac delta function. Okay, so what is this unit impulse input? Let's say we consider u of t to be a signal of this particular form. Okay, let us say at around time t equals 0 for a very small time interval, let us say minus epsilon by 2, 2 plus epsilon by 2, the magnitude of the signal is 1 by epsilon. So, immediately we see that the area of this rectangular signal is 1, right. So, that is how the adjective unit comes into being, right. So, then let us say like we shrink this epsilon and make it tend to 0, right. What is going to happen is the following, right. So, the input is essentially going to just jump to a very high magnitude instantaneously and come back to 0 instantaneously. Okay. So, this is what is called as the Dirac delta function, which is essentially denoted by delta t. Okay. Delta t is the unit impulse input. Okay. So, so essentially we want to provide, let us say suppose if I provide the unit impulse input as the input to the system, the corresponding output is what is called as a impulse response. Okay. So, what we get, of course I can also say unit impulse response, okay, in general. So, what is unit impulse response? Unit impulse response is nothing but the output of the system when I provide a unit impulse input to the system. Okay. Another input which is typically used in systems analysis is what is called as a unit step input. So, what is this unit step input? So, as the name suggests, like so we have, let us say time t and u of t. What we are going to do is that like at time t equals 0, we give a step input to the system that is of magnitude 1. Okay. So, this is what is called as a unit step input. So, the output that we get from this system is what is called as a unit step response. Okay. So, that is the output of the system when we provide a step as the input. Okay. So, we see that the impulse response and the step response are going to be very valuable to us, okay, like as we go along, like we are going to use them in lot of analysis, right. So, the third standard input that we would consider is what is called as a unit ramp input. What is this unit ramp input? Unit ramp input is nothing but u of t is equal to t. Okay. So, that is what it is. Okay. So, that is a unit ramp. So, the input just scales like t. Okay. So, that is why we call it as a the slope is 1, that is why we call it as a unit ramp input. Okay. And the fourth standard input that we typically provide, of course when we provide the unit ramp as the input, like the output that we get is what is called as a unit ramp response. Okay. And the fourth class of inputs that we typically provide are what are called sinusoidal inputs. Okay. Sinusoidal inputs, as the name suggests, we provide sinusoidal functions as inputs of varying frequencies, cos omega t, like sin omega t, like we are going to have input which are going to be cos and sines, right, whose frequencies are also can be different, right. And because we will later see that if we have what is called as a stable system, right, stable LTA system, the steady state output of such systems when we provide a sinusoidal input is also going to be a sinusoid of the same frequency, and that information is used in analysis, and that analysis that we do is what is called as frequency response analysis. Okay. So, frequency response has to do with like what we study about the steady state response of stable LTA causal systems when we subject them to what to say sinusoidal inputs. Okay. So, that is what we are going to look at, right. And so these are four common inputs that are typically provided: impulse, step, ramp, and sinusoids. Okay, of course, in general, an input can be any arbitrary combination of these inputs, and that's where linearity helps us. Like, see, there are two reasons why we study the response of systems to standard inputs, so that like we have a uniform baseline to study systems, and also we extract and define parameters for system performance which are based upon one type of input, right. So that's very important, okay, so that we can quantify system performance. So that's something which we are going to see. We will see that we are going to use step response and frequency response to essentially define parameters that quantify system performance. That is one reason. And second, like in general, any arbitrary input can be usually written as a linear combination of these inputs. So since we are dealing with linear systems, like once we know the output to these standard inputs, we, in theory at least, like we can calculate the the output to any arbitrary input that we provide. Okay, so that's another perspective of why we study the these standard responses. Okay, and before we return back to the discussion on Laplace transform, okay, we just discussed these standard inputs, and there are two important aspects that are critical in control design. Okay, so let me point them, discuss what they are. The first one is what is called as stability. Okay, so we want to design stable systems, okay, and if a system is unstable to begin with, we want to stabilize systems using feedback. Okay, that's one reason why we design control systems. So whenever we design dynamic systems of the class that we are considering, first we want those systems to be stable. Okay, so we'll shortly define what notion of stability we are going to use in this particular course. The second thing is, once we design stable systems, we want to evaluate how those systems perform. So we are going to be interested in what is called as performance. Okay, so for us, stability is first of all paramount. Once we have stable systems, we worry about performance. And the notion of stability that we are going to use in this particular course is what is called as bounded input, bounded output stability. Okay, so what does that mean? It's abbreviated as BIBO. Okay, that's the abbreviation of bounded input, bounded output stability. Okay, so what is meant by bounded input, bounded output stability? Please note that our visualization of a system is an entity to which we provide an input u of t and we get an output y of t, right. So that's our visualization of a system, right. What bounded input, bounded output stability says is that if I provide any bounded input to the system, the corresponding output should be bounded in magnitude for all time. Okay, so that is the notion of bounded output, bounded output stability. Okay, so let me write down the definition. So a system, of course belonging to our class, is said to be BIBO stable if given any input u of t such that the magnitude of u of t is less than some positive real scalar m, which is obviously finite. That's what this means. Okay, for all t, if given the system output, the output of the system is always bounded in magnitude. So that is magnitude for all t. Okay, that is the magnitude of y of t is less than or equal to some n less than infinity, okay, for all t. Of course, here m and n are finite, positive, real numbers. Okay, so that's what they are. Okay, so this is the notion of bounded input, bounded output stability. Okay, that's what we will consider in this particular course. Okay, these ideas are extremely important. Okay, like so when we design controllers, we want to ensure that the system that we design, the closed loop system that we design, is first of all stable in this sense, and then it performs. Okay, and how do we get performance? For performance, we are going to use a step response, impulse response, frequency response, and so on. Right? We will learn about them as we go along. Okay, so but this is something which is extremely important. Okay.